Hey guys, let's analyze a mass on an inclined plane. So let's draw it really big. Okay, so here we go. We have a mass on an inclined plane. Okay, and we'll assume that for now this is frictionless. Okay, now let's call this angle theta. This block, let's say, has mass m. Okay, so let's analyze the forces acting on the mass first. Okay, so even before that, let's choose an axis. So when you have a system like this, right, when you have an inclined plane, okay, so the easy thing to do is to tilt your axis as well, okay, because any vector pointing down is positive, any vector pointing up will be negative. So you have to make that decision because your coordinate axis gives you the signs of your vectors, right? So that's why making that choice is important. So we chose our axes as down being positive and up being positive y-axis. So this is like this follows the convention that right is positive, left is negative, up is positive, down is negative, right? So this is our axis, right? So let's look at the forces acting on this mass. Okay, we'll just draw the forces on the mass itself. Okay, so the weight acts straight down, okay, and the normal force will act perpendicular to the surface, okay. Remember, normal force is always perpendicular to the surface, okay, and weight is always straight down, okay. So one thing that confuses students in these questions is that um, this angle, now we'll resolve the forces, right? We will resolve weight in this case, okay? Because our axes are tilted, right? We want our components along the x-axis and along the y-axis. The normal force does not need to be resolved. It's already along the y-axis. We need to resolve the weight, okay? We need to find what component goes over here, what component goes over here. For that, we uh, we need to know this angle, okay, this angle over here, and this angle turns out to be theta, and that confuses students a lot, right? So let's look at this. I'll give you an argument. I hope that satisfies you. um, so the idea is that if this angle, if two lines make an angle theta, this is from geometry. Now if you draw a perpendicular to this line, okay, and a perpendicular to the other line, which is the ground in this case, these two lines will also make an angle theta with each other, okay. It's just like you have tilted the if you tilt the page, your inclined plane is this will just be your inclined plane tilted, okay. You've just rotated your inclined plane, in other words. So so that's why this angle is also theta, because this line is perpendicular to the inclined plane and this line is perpendicular to the ground, okay, the line of the vector weight, okay. So now let's draw this again over here because it's a bit messy over there. So let's look at the components. So here's your mass, here's W, here's the normal force. Now again, this is theta. So remember that the side closest to the angle always has a cosine, so this is W cosine theta and this is W sine theta, okay. So you can show W sine theta over here also. It's the same thing. It's actually acting on the object, so it's good to show it over here. So got it. So now we know the components. We know that W sine theta goes along the positive x-axis. W sine theta goes along the positive x-axis. W cosine theta goes along the negative y-axis, and normal force was already along the positive. So now we can write Newton's second law. So Newton's second law along the x-axis is just, so F net, you can give that subscribe. equals mass times acceleration in the x direction. So let's say that the object is moving down with has acceleration a. So so then f net x, the only force acting is w sine theta in the x direction. So you get m equals m times a. So this is mg sine theta. So this is equal to a. M cancels out, so a equals g sine theta. So it's independent of the mass of the object. Interesting, right? No matter if it's a car skating down, let's say an icy surface, or a truck, they both will have the same acceleration. Okay. And this is also irrespective of the direction in which the object is moving. Okay. So let's say that the object is moving up the inclined plane. Let's say it has velocity v. Its acceleration is still down the inclined plane, but now since acceleration and velocity have opposite directions, this will be deceleration. Okay. Remember, deceleration is always when acceleration and velocity point in the opposite direction. When it's moving down the inclined plane, let's say in this case, it will be this will be acceleration. They both point in the same direction. So no matter what, if it's frictionless, remember, if it's frictionless, then it's always going to, acceleration is always going to point down the inclined plane. And another thing is that you would see sometimes acceleration is negative g sine theta, right? When is that the case? So that can be when, if you flip your axes, which is of course something we don't do, but you can in principle. Of course, you can take positive x over here and positive y over here. Okay, then your object is moving towards the negative x-axis, so your acceleration points towards the negative. So if this is your convention, if you choose this as your axis, then a points down towards the negative, so a equals negative g sine theta. And another case where, another scenario in which acceleration can be negative is when you choose your inclined plane to point in this direction, let's say. Okay. So then, and if you stick to your convention that right is positive, which I usually do, I stick to this convention that right is positive, up is positive. So then if you make your inclined plane this way, then your acceleration will point towards the negative x-axis, and your acceleration will then be negative. So in this case, a equals negative g sine theta. Okay, so in general it can be a equals plus minus g sine theta. That's what that's how some books will state it. Okay, so this was the object on an inclined plane. On a frictionless inclined plane, we'll introduce friction in later videos. So hope you liked the video. Please subscribe, and if you have any question, post them in the comments. Thank you.